Hello, welcome to our IRA seminar. It's my great pleasure to introduce today's speaker to you, who is Christian Rupprecht. He is currently a postdoctoral research fellow at the Visual Geometry Group in the University of Oxford, and he holds a PhD from the University at Munich, and he also spent some time at Mila in Montreal. Christian's work has already garnered quite a bit of attention. If I pick out a few highlights, his joint work on supervised 3D reconstruction has been awarded the Best Paper Award of this year's CVPR. And it certainly did not escape our attention that he was part of the second place team of our inaugural NeurIPS traffic forecast competition in 2019, which boasted a thought-provoking entry that, very honestly, in part also helped us redesign this year's competition. I would like to say that if you want to ask questions during the talk, if you're on Zoom, you can do so by putting it in the chat, or if you're on YouTube, you can also put it in the chat, and I will try and ask the questions later on. Well, without further ado, I'm very much looking forward to your talk, Christian, and I hand you the floor.
Thank you very much. I'm excited to be given the opportunity to give this talk to you today. Let's get right started. Okay. I just assume that everything is working fine and you would interrupt me if there were any technical problems.
It is working fine.
Okay. So my talk is titled Visual Learning with Reduced Supervision. What is this all about? Supervised learning is being used everywhere now. It's recommending our products, it's in our cars, it's recognizing the speech, it's helping doctors, it's in robots, vacuum cleaners, it's manipulating us on social media, and many more applications are out there. And what all these systems have in common is that they need to be trained with data. And very often this annotation data that is needed to train these algorithms comes from humans, which is in most cases quite expensive because you need tons of data, and humans need to go and annotate every single sample. And that's, of course, slow, and for some tasks, it's even impossible to annotate everything. So I have designed a little diagram that looks like this. This is where most algorithms that we're nowadays using for machine learning look like. So you have a certain amount of data and you have an equal amount of labels. And what I've been interested in the last years is to change this balance as much as we can by reducing the amount of human supervision that we need to train these algorithms. So it would be very nice to move to a regime where the distribution looks like this, where we have a lot of data, because now we can very easily collect a lot of data since we don't need labels. And the amount of labels is as small as possible. And of course, shifting this balance cannot come for free. So what we need to do is we need to increase the amount of priors that we instill in our models to compensate for the lack of labels. So the idea of priors is basically that we build into our models a way of understanding how the world works, and that replaces the need for labels, because then the algorithm doesn't have the need to pick up all these things, how the world works, from the labels, but it can just has it built in, and that acts as a replacement. So to dive into the first part of the talk, I want to talk about a example, and that is titled How to Make Tea. And if you think about some kind of robot or system that you have to build and you have to send out into the world to make tea in people's homes, you are immediately confronted with a problem, because everybody's home looks different, and also the way that people make tea is different everywhere, and you are confronted with an unlimited variation of these combinations in the real world. So what we need to do is we need to find robust representations in our algorithms that are able to deal with all these variations. And one topic in computer vision that tries to learn these very general representations is naturally called representation learning, which is the first part of the talk today. So in representation learning, the idea is, as I said, to learn a very general representation. For example, in this case, I talk about images, but you can also do it for videos or audio or any other kind of modality. So how the task is set up is that you are given a data set, in this case, ImageNet, with 1 million images, but 0 labels. And now you have to train a neural network that learns very generic representations of this data. So you have to come up with what is called a pretext task. This is any task that you can imagine to come up with that trains the weights of a neural network. In this case, I put an early example of the field, which is called RotNet, where the input image gets randomly rotated in increments of 90 degrees, and the network just has to recover what this rotation was. And this sounds easy, but actually requires the network to do quite a bit of image understanding to figure out where is up. So it has to basically figure out what is the object in the image and where is usually the direction that this object is represented to be able to figure out what rotation that is. And then to judge whether we have learned a general representation that works for a lot of different tasks, the way to evaluate the representation learning is usually by fine-tuning on a lot of different downstream tasks. And the idea there is that if you have learned a good representation in the first step, then you will also get good downstream task performance in a lot of different tasks. So to express this in the diagram I had shown before, it looks now like this. So we have a lot of images, 1 million in the benchmark cases, and no labels at all. And the way we build in priors into the system is through these pretext tasks. We're trying to build a task that already instills a lot of information about the world through these pretext tasks, how they're being designed. So when we started looking at this topic last year, we asked ourselves, okay, we have 1 million images, and this is currently already working quite well, but how much information is there really in 1 million images? And the way we came up to test this knowledge is by going the other direction, in asking the question, what can we learn from a single image? Basically, how much information can we extract from a single image, and how much does that compare to scaling up to 1 million images? So now the data column is very small, and we still don't have any labels, but now the way we deal with one single image is through augmentations. And what I mean by that is the following. So we take an image, for example, this was one of our test images, and to be able to train a neural network with one single image, what we do is we extract 1 million patches with different rotations, color changes, squeezes, and so on from this image. And then we basically artificially generate a data set of 1 million images that all come from the same original source image. And then with this synthetic data set, what we can do is we can take the state of the art in representation learning methods and just train them on this synthetic data set that we have curated. And then we can see how that performs. So if we first look at, so this is an example of a deep cluster, which was a method that was state of the art at the time where we did this work. And as you will see later, the state of the art in this field is moving so quickly that basically every month the picture changes. And here we have evaluated this method at different depths of the network, so different convolutional layers. And you can see that in the beginning, when we compare to the feature quality of supervised learning, there's not a big difference, but towards the end, the gap becomes bigger. And now we compare this network that was unsupervisedly trained on 1 million image to the same algorithm trained on just one image. And the results were relatively surprising. In the early layers, there's basically no difference between the method trained on one image and trained on 1,000,000 images, whereas towards the end, there is a gap. And this results in two observations. The fact that there is no difference in the early layers is another proof that these early layers of the neural networks do not really learn any semantics about the real world, because you cannot learn semantic information from a single image. There's just not enough variety of different objects that there's really semantics in there. And although there's a gap in the later layers, the gap is not as big as we would have expected it to be when you move from one image to 1,000,000 images. And that leads us to believe that there is indeed a margin where we can improve, because the amount of information that you add during training when you move from one image to 1,000,000 images is massive. So the performance gain between moving from one image to 1,000,000 images should also be much bigger than it is. So to move now to general representation learning, I want to give a quick overview what is the current trend in representation learning. So the main algorithmic idea that a lot of papers are currently using is called contrastive training, which is a very intuitive and nice idea. The idea is you take your image, you pass it through your network, you get a feature representation, and then you take your image and perform an augmentation. So for example, a rotation or a flip or a contrast change, cropping, and so on. You pass also this image through the network. And then your constraint is that since this is originally the same image, just with different augmentations, these images should lead to similar feature representations. And training this alone would not be enough, because then every image would have exactly the same feature. So you also need a second force that acts as a training signal. So what you do is you take a random other image and say the feature that comes from this other image has to be far away. And you can train this relatively nicely with a softmax formulation, where you basically just say that one image should retrieve its augmented version and all the other images act as negative classes in this retrieval problem. So this means that basically every image is a class, and its different augmentations are different instances in this class. And it's very clear that the augmentations for these methods are very critical, and we can see that I also later have a graph where changing the augmentations almost gives more difference in performance than changing the actual underlying method. And this is an indication that these priors that we're building in the models are very, very important, sometimes even more important than the actual technical parts of the method. And usually these methods need a very large batch size, because you can already see on the left there, the example that I've given, the manatee and the zebra are very different images, and it's not very difficult for the network to figure out that these should actually not be the same. So you need large batch sizes so that you have actually hard examples in your training at each training step, because the easy ones, it separates very quickly, and then you need actual useful signal. And I said before that this training regime is a very popular way to train these unsupervised methods that currently reach the best performance. So here's a couple of examples that all have various different ideas of how to exactly implement this, and I would recommend checking out these papers. So when we looked at this gap in the deeper layers between performance, where we said, okay, now that we have 1,000,000 images, we should actually get a substantial improvement. We thought about what the biggest difference is between supervised and unsupervised representation learning. And the obvious answer to that is the labels. So the question we asked ourselves next was, can we actually come up with labels during training? Because if we had labels, then the problem would be very simple. So to look at this in the diagram, now we have 1 million images again. We still don't have any labels, but we actually want to learn labels. And a very natural way to assign labels to unlabeled data is through clustering, because if you cluster data together, then this basically means that you give all the images that cluster in one cluster the same label. So this is a sort of a chicken and egg problem, because you are on one hand trying to predict a label for every image, but to train this, you actually need to label image, and you want to do this at the same time. So you have this typical chicken and egg problem. Now comes a very short part about math. So don't be scared. This is just typical supervised classification. We have images. We push them through our network, and our network is parameterized with a typical theta. And out comes, as in supervised classification, a probability distribution over the possible labels. And we learn this with a popular cross-entropy loss that everybody is using these days, where y are the dataset labels, and then you're just minimizing this loss. So if we also want to learn the labels with the same loss, we first have to do a short mathematical trick where we rewrite the loss like this. It does exactly the same thing as before, but now Q is actually a label lookup table where we have basically a 1 wherever the ground truth label is assigned to this image and zeros everywhere else. And then to make this actually trainable, we just need to relax this lookup table and transform this to a label distribution that is then continuous. And that allows us to actually learn the labels with the same loss that we would actually learn the classification and the network. But if we do this naively, and this is a concept that will come up a couple of times in this presentation, the network learns to cheat. And this cheating in this case is expressed in the way that it assigns all the images to the same class, because then it can very easily solve the prediction part by just always predicting the same class, and the assignment part is also very easy. So to prevent this, you have to introduce another prior, and in this case, we chose the prior that all the classes or clusters have an equal number of images. This is relatively easy to introduce just as a second part of the loss. And suddenly it becomes very hard for the network to cheat, because it has to distribute all the labels, all the images over the clusters. So the whole thing, as a typical chicken and egg problem, is a alternate optimization problem, where we start with assigning labels to images first. So we take the untrained network and minimize this energy that we've seen before. And if you squint at this energy really hard, you basically see that this is an optimal transport problem, and there exist algorithms that basically solve this assignment problem very quickly without any big computational effort. So this is exactly what we want. We run an optimal transport problem solver, get a label for every image, and then on the other side, we just train our CNN as we always do by just minimizing the cross-entropy loss between what the network predicts and the assigned labels. And once we've trained an epoch, we go back and update our image assignments. At the time, we got state-of-the-art results with a method that was relatively different than existing methods, because it was based on clustering instead of the typical contrastive. But as I said before, the field is moving very quickly. And what is interesting in this graph, if you look at it, there are several methods there that have a little V2 behind them, which most of the time means they just changed their augmentation strategy and then get a bunch more better results. And that, I think, is very interesting, because that means the priors are almost more important than the actual underlying learning method to improve the results. I've colored in blue all the methods that do the contrastive training that I mentioned before, and the orange methods use some other way. Most of the time it's clustering. Older methods have a bunch of more creative ideas. What I find compelling about learning to cluster is that it becomes a little bit more interpretive. So you can actually go and look at the clusters that your method has discovered. So here I'm going to visualize a couple of clusters, and what I mean by purity underneath the cluster is basically how pure this cluster is in terms of ImageNet classes. So if purity is 1, then all the images in this cluster belong to a single ImageNet class, which is basically what we would like from a perfect clustering method. So there are very easily interpretable clusters like the zebras or other semantic clusters that are a bit more difficult to recognize. This is, for example, Australian football. But there are also other clusters that are not very pure in terms of ImageNet classes, but that are still very pure in terms of semantics. So here's this baby cluster that we found that is comprised of images of ImageNet that contain babies, but are spread over different clusters. So this is bassinet and crib, where some of the images contain babies, and these baby images then have been clustered all together. Of course, there's also lower level clusters that this one seems to respond to dark circles or ovals, or these kind of bar patterns that we see here. And then there's a couple of clusters that we really also don't know exactly how they formed. My colleagues in Oxford have made a very interesting publication at NeurIPS this year that analyzes how much these clusters are interpretable and how they can be rated and understood. So since we called the previous method on images self-labeling, there was basically a need to apply the same method to videos, because then we could write a paper that is called C'est la vie. So this is exactly what we did. But the interesting thing about using this algorithm on videos is that in videos you have multiple modalities. And additionally, in contrast to a lot of image data sets, video data sets usually do not follow a uniform distribution. So if you look at this, there's a very long tail distribution of a number of videos in each class. So we had to extend our algorithm. And basically, the idea here is that we run audio and video through separate networks, but each network still has to predict the same cluster. And that basically makes the algorithm robust to really looking at both modalities, because both modalities need to inform the label equally. And additionally, there is a mathematical trick that you can do to allow arbitrary distributions that you can specify for your size of the clusters. And what is interesting there is that in terms of video representation learning, there's methods that work really, really well and get very high scores in representation quality. But if we take their representations and run k-means to actually get clusters, and then compare the clustering performance to what our method that intrinsically does clustering during training. So if we compare these methods, it turns out that if you do clustering during training, you would get better performance, even if the features you do the clustering are originally better. So looking at some results again, you can see that in most of these examples that the method finds in terms of clusters, the audio and the videos corresponds. So you usually have instruments that cluster very well together, or different kinds of noises like the fireworks or police sirens or cats. All these videos, both the visual part and the audio part informs the clusters, and you get these very nice and pure clusterings. So to answer the question of the first part of the talk, can we learn to label data without labels? The answer is very much yes. And even without using any labels during training, if you then, during evaluation, just map the learned clusters to ground truth classes, you get a relatively high performance. And I like clustering because it discovers structure in the data, and that makes your whole algorithm a bit more interpretable, because in the end, you can actually look at the clusters and see what's happening instead of just looking at the performance curves. And as an application, there is a very nice potential to reduce the labeling effort, because you could run one of these grouping algorithms on your data, and then instead of labeling every single sample in your data set, you could go and just show the clusters to your annotators. And that greatly reduces the effort to label the data set, because now you're not annotating one sample at a time, but you're annotating whole clusters at a time, which is much more efficient. And in the terms of video data, I have shown that exploiting the multimodal data really helps to learn very nice and semantically meaningful clusters. So since this is the end of the first talk, I wanted to quickly advertise a workshop that we were running at ECCV this year, where a bunch of the big shots in the field of representation learning gave their opinions on what is supposed to be the next big problems in the field. And the videos are on the website, so if you're interested in this topic, you can watch their thoughts on the matter. So for the second part of the talk, I wanted to change the picture slightly and move to the field of 3D from a single image. This is in computer vision a very old problem, and we were trying to give a new spin on the topic to see how much supervision does this field need. So traditionally, what people have been doing is when they want to learn 3D from a single image, you can use, for example, ground truth data or shape models, multiple views. You can use special sensors like range sensors. You can use the segmentation maps and do some kind of scene carving where you carve out from multiple views the object. You can use key points, camera viewpoint, you name it, anything is possible as supervision. So as a typical academic challenge, we said, can we do the whole thing without any of these supervisions? And that led naturally to this question, how much supervision do we actually need to learn the nature of 3D objects? So to come back to my diagram, now we have collections of single images, and we do have a little bit of labeling in the sense that we know that all the images come from the same object category. So all the images are, for example, faces. And the second bit of supervision comes from the fact that we want to reconstruct symmetric objects. So not only do we know all the images come from one category, we also know that this category is a symmetric object. And to make this work, we have to build a bunch of priors into the system, and they are mainly shading the symmetry that I mentioned before and how rendering works. So here's a concrete example. In this case, it's cat faces. So we're given this data set where we have one image per cat, no other supervision than that, no 3D information at all. And then we run our algorithm and we're trying to reconstruct the 3D shape of cat faces like that. And there are two main observations that go into this work. The first one is that this fact that we're reconstructing a symmetric object category is very useful, because if you would know the correspondence between the symmetric parts of an image, you basically get a second view for free during the reconstruction. The problem is that, of course, you don't know these correspondences, so you have to figure them out. And the way we deal with this symmetry problem is that we reconstruct what we call a canonical view. And in this canonical view, the image is actually really symmetric along the vertical axis. So you can flip it left to right. And the second observation that went into this work is another very old observation in computer vision, where we know that shading gives you a very strong cue about the underlying shape. There's a lot of work where people change the camera viewpoint, for example, the light viewpoint, and then compute from the differences in shading the underlying shape. So if you're approaching this topic, you have images from a single category, you want to reconstruct 3D, and you don't have supervision. The first idea to approach this problem is you take your input image, and then you decompose it into the parts you're interested in. So you reconstruct a 3D viewpoint, some kind of depth representation, or 3D representation. In this case, we chose a depth map and a texture. And then you give these three things to a differentiable renderer that reconstructs your image, and then you're minimizing the reconstruction loss. Unfortunately, and as I said before, these methods like to cheat and find the easy way out. So what happens if you do it like this is that your depth map becomes flat and the viewpoint is 0. And then it's basically just copying the input image onto a flat plane and rendering it right in front of the camera, receiving a perfect reconstruction loss, but you actually have not learned any 3D information from this. So the way we deal with this problem is through this symmetry constraint. So what we do is we introduce some kind of noise into the reconstruction process. And we do this by just randomly flipping the depth and the texture map. And this distraction that is introduced into the network at this point means that to be robust to this random flipping that the network cannot anticipate, the only way that you can solve this is by making these reconstructed maps symmetric along the vertical axis. Because if it's completely symmetric along the vertical axis, then the flipping actually does not change the image. And this trick forces the network to actually pick up a proper viewpoint, because once you have the depth and the texture in this canonical space where it's symmetric around the axis, then the viewpoint has to come in to be able to reconstruct the image from the proper viewpoint. However, there's still a small problem, and that's the fact that when you flip the image, you're also flipping the light to the other side. So if you would reconstruct an image from its flipped version, then suddenly the light would be coming from the wrong side. So to fix this, we add the light as one of the predictions, and then build a shading model into the rendering pipeline, where we basically compute the shading from the 3D and then shade the albedo that gets predicted. And that removes the lighting problem. And then finally, there is another problem with the typical object categories, which is that although the whole category is usually symmetric, there are parts that are not symmetric. And for human faces, this is usually the expression and the hairstyle that are not completely symmetric. So the way we deal with this is we add a prediction part in the network that predicts the confidence of the reconstruction. And we reweigh the reconstruction loss with this confidence. And this allows the network to discount the factors or the parts of the image that are not going to be symmetric. So you can see relatively well here that the method has discovered which parts will not be reconstructed very symmetrically, and discounted these parts in the reconstruction. So looking at a couple of results, we find that only half of the animation is playing. Now, sorry about that. We find that the reconstruction quality is surprisingly high, given the fact that we have not used any 3D supervision during training. And the second, maybe more interesting observation is that the model that was trained on human faces generalizes to all sorts of different modalities. So you can see we can reconstruct the Mona Lisa, all these paintings, cartoons, emojis. And the cat model also generalizes to very different cats that we have seen. And we are convinced that this very nice generalization capability comes from the fact that we have built so many priors into the model. So the network has really learned how to extract all the necessary information from the image, even if it's a reduced fidelity input like the cartoons or the sketches. So to answer the question, how much supervision we actually need to learn, in this case, symmetric 3D objects, it's not very much. And as I said before, we get very good generalization, even though we don't use any labels, or maybe because we didn't actually use any label data. I've explained how the priors that we built in prevent these failure modes where the network learns to cheat by just minimizing the loss, but not actually solving the problem. And this is a very typical way we design these methods, by finding good priors that stop these degenerate solutions. And for faces, there's of course a lot of models out there, supervised models that have amazing quality that is much higher than what we can achieve without supervision. But we think there are several cases, for example, animals, where it's very difficult to acquire proper ground truth, because you cannot make animals sit still in 3D scanners to acquire all the data that you need. So to conclude these two examples and my presentation of the day is basically to answer the question, where do we move here in the grand topic of reduced supervision in computer vision? And since we're just starting with this, there's still a lot to do. And one of the main next challenges I think that we need to look into is the topic of uncurated data sets. Because currently what we're doing is we are doing unsupervised learning on all these data sets that were specifically constructed for supervised learning. So we're training on ImageNet, we're training on the face data sets. And even though we are not using labels, we are still using the fact that a lot of work went into building these data sets, curating these data sets, selecting proper images and so on. So we need to move to data sets that are much less curated, but then we're immediately dealing with the next problem, which is long tail distributions. So in the real world, we have this problem that there's a couple of classes, categories, types of images where we will have tons and tons of examples. And then there's a very, very long tail of objects, categories, where we only have very few examples. So we need to build algorithms that are able to deal with this hugely imbalanced data and still produce reasonable results. And then going back to the T example that I brought in the beginning of the presentation, is the fact that once we move our algorithms out to the world where they solve real world problems, we definitely will start making mistakes, because all the situations will always be different to what we've originally trained on, and then we need to adapt. And this adaptation then leads to all these problems that come with continual learning and non-IID data, where now our samples come continuously over time and not just randomly sampled from a data set. On the side of tasks, I think there are several tasks that are very interesting and can be solved with much reduced supervision in the next couple of months or years. And just to name a few that I think are very prominent next candidates to do unsupervised, I think detection, segmentation, action recognition could be good candidates to work. And then, since we're moving or heavily dealing with data and no labels, what is very important to have in mind, and something where the community also needs to pay more attention to, I think, at the moment, is bias and privacy. So since we're basically training algorithms only on the data without labels, we are very susceptible to picking up all these biases and privacy issues that are in these data sets. And we actually need to spend a considerable effort to build algorithms that don't fall into these traps and have these issues that maybe our data sets have. And with that, I think my time is over and I'm happy to take questions.
Well, Christian, thank you very much for a really great talk. In fact, I have a lot of questions, but I think I'll give the floor to other people first. Let me not be too selfish. So the first question we actually got is, can we create 3D base maps from satellite imagery? I guess that would be a very large scale endeavor.
That's a very concrete question. So
yes. This may indicate that they're members of a mapping company on this call.
Yes. So the good thing, I think, about satellite images is, I'm not an expert in this area, so I might be saying something wrong, but you have a lot of priors there that you can use to improve your reconstruction. I'm, as I said, not an expert, so I don't know what's being used, but of course there is, again, shading, since these images are usually taken on bright sunny days because you don't want clouds. And so you could use shadows and all these things. I assume, but I don't know, that there's a lot of priors that you can exploit that are in the data that are not being used at the moment. And being in academia for me means I'm trying to push things to the limit, in the sense that we were trying to reconstruct these faces without any supervision. But of course, if you're a mapping company, for example, that's not exactly what you want to do. But what can definitely help is that you use the data with the labels that you have, and then add these priors on top to actually improve the results that you have, and not completely replace any annotation. Because if you already have these labels or annotations, then there's not really a reason not to use them.
Yep, very nice answer. I have another question, which is asking concerning the priors on ImageNet, that all clusters have to be balanced. This might be very restrictive for many applications. Did you try other priors?
Yes. So in the second work on videos, we actually found a way how we can relax these priors. So you can basically, with this trick that we invented there, use any prior distribution during training. In the original paper on ImageNet, we did a couple of experiments. We didn't have enough compute to do them fully on ImageNet, so we did them on CIFAR, where we artificially rebalanced the data set, and we had, I think, 10 times more examples of trucks than frogs.
Okay.
And that was not really a big problem for this method, because the way we do the clustering is that we usually overcluster the data set anyway. So in ImageNet, we cluster in 3,000 clusters. instead of the 1,000 categories that are there. So even if there is a moderate imbalance, then this overclustering solves the problem. But algorithmically, the more elegant way to solve it is actually to use the second method that can deal with any prior. So that would definitely be the way to do it.
Vanessa, we have another question, which closes with from S3 and here. So I guess it is a mapping question again. The symmetric, non-symmetric discount image is kind of an attention.
It is kind of an attention in a way, but so the trick is that it's self-balancing. You could see this loss basically as a Gaussian, where you are optimizing the difference as well as the sigma of the Gaussian. And the nice thing about this property or about this loss is that the minimum is basically either where your error is 0 or where the sigma is the same as the error you're making. So you're not running into these situations where the optimal solution is to just discount the whole image and nothing happens, but is actually really trying to reconstruct the image as much as it can and only use this discount factor whenever it's really needed. So that's the way it's able to really find out where the regions are that are not symmetric and only discount those.
Yeah, very good answer. The question continues here. Is there temporal connections in the videos that you show?
No. So since we trained only on images of single images of the category, I can also go back to this video if that works. This is really frame by frame evaluation, so there's no extra consistency that we built in, and it's relatively smooth. You can see when the person that is speaking is turning the head, you can see in the bottom reconstruction that the light is actually changing because it's basically a different viewpoint. If you're turning your head but you have the still reconstruction, then what's actually happening is that the light is moving.
Very cool. I think one other question, have you tried other data sources like text data and essentially use this method as in like a bit like topic modeling?
Yes, so we have not yet done that, but it's definitely on our list. So because text is very attractive also in the sense that with the text, you start getting some semantics back. If you just have a video and audio, then you don't really have yet any semantics that tell you this cluster is a cluster of cars or this is a cluster of fireworks or something. But once you add the text modality, you can actually start naming things, because then also all the texts about fireworks would start grouping together. And I think this is a very promising direction to add even more modalities and then also recover some kind of semantics from the combined richness of information there.
Very nice. Going in the same direction, NLP clustering priority is usually much lower than 0.9. Should you expect some concepts to work in a similar manner / success?
I think I need a little bit more information on this question.
Okay. Yeah, we can give the author some more time to maybe verify. I have
because I'm not an NLP expert. I actually don't immediately understand what the question is about.
Very good. I can't guess either. So and I'm certainly not an expert. One question I had, so I understood this correctly. The number of labels you guess is predetermined, right?
Yes.
It's not that the clusters, in some Bayesian way, they kind of find out how many they get. And can you give a bit of like a feeling in how heavy the compute is in this sort of, I think you call it chicken and egg, I would call it pulling oneself out of the swamp, like Münchhausen, like this loop you had? I mean, is it like, I mean, it's hard to say because it depends on the compute infrastructure, but it's very heavy, not very heavy.
So we were actually surprised how lightweight it is compared to training. So this label assignment solving this optimal transport problem, there's this nice approximate algorithm that is called the Sinkhorn-Knopp algorithm. And if you implement that on a GPU for assigning labels to the whole ImageNet training set, it takes about 5 minutes.
Wow.
So you spend much more time actually training the network for 200 or 400 epochs than you spend clustering at every step.
Very nice. And how many of those cycles between, so one cycle being training network and then as well, I guess first getting the labels and then training network, did it take?
So in our experiments, we found that there's basically, it always gets better if you do it more. So it does not degrade at least. But of course, you don't want it too much because then it really becomes a computational burden at some point. So the way we found a good middle ground of this is that we have some kind of exponential schedule where we do it relatively often in the beginning and then reduce the amount. And this follows this typical intuition that in the beginning, everything is very vague and nothing is really assigned properly to the right cluster. So you want to run it very often to actually allow the labels to change a lot. And then once it becomes more stable, there's not really a need to recompute at every point. There is probably an opportunity to somehow decide this dynamically by evaluating some kind of energy at some point or classification score to dynamically decide when you want to recluster or not. But we have not done it yet. So it's open if there's a better way than a predefined schedule.
Very nice. Very nice. And just the last one for me, and then I'll stop being selfish. So the number of labels, I guess you had, where I saw you using 1,000, I guess from ImageNet, 3,000 for this extended thing. How far, I mean, how many labels do you think this method would stretch to, or do you see any deterioration if I say I do 1 million labels and keep going? If the data set's big enough.
Yes, so the only problem I think this has is the typical problem that if you have 1 million labels, then your last fully connected layer becomes relatively intractable, and you have to do the typical tricks of not building it completely, but subsampling at every step in time. That the people that actually do these highly multi-class problems do. And yeah, of course, it has to be somehow correlated to the size of your data set. Because if you, at some point, you have so many classes that basically every image is its own class, and then you're back in the contrastive training regime. And I think that's also a very nice intuition that this contrastive training, what it does is it makes every image its own class. And this is actually very useful if you don't know what the downstream task is, because the moment you start grouping is you're starting to throw away some information because you're grouping things together.
Yeah.
But if you say every image is its own class, then you keep as much information as possible, and only the augmentations tell you what you are allowed to throw away. So there's a merit in both directions.
Very good. I have another question, which I think you've partially answered or even completely, but I'll ask it anyway. What alternative have you considered to the overall prior weights?
To the overall prior weights?
I think all different priors you have considered. I think you mentioned something earlier where someone asked whether the uniform one was the...
Yes. So we played around with a couple of typical Gaussian, uniform, Zipfian in the size of data sets that we could handle in this work, there was basically no difference between Zipfian distribution and Gaussian distribution, just because if the tail is not long enough, you don't really have a big difference in these two distributions. But that's also encouraging, because it does not mean you have to really estimate your distribution super precisely to get the best possible results. So you can make a good guess, and then it's probably fine.
Good. There's a question we actually got from YouTube. I should mention that on YouTube we have a maybe 30-second delay. So the annoying problem with contrastive learning doing better with large batch size is that suddenly papers need a TPU due to memory demand. Can you comment on the cost of research? Very applied question.
Very applied question, yes. And of course, being in academia, not at a big company, I also suffer from these papers that get very good performance. I think there's a balance that it's not too bad. It forces the academia to think about solutions that are not as compute heavy. And clustering could be one of these solutions. So currently we're again outperformed by the contrastive training methods. And it's also really hard to compare, because everybody, of course, has different augmentations and trains differently long with different batch sizes. But performance is not everything. Even if some reviewers think that this is the only way to judge a method, I think there's also merit in coming up with interesting methods that might not exactly be top performing in all metrics.
Good. I just realized that maybe earlier on I misconstrued a question, so I apologize profusely to the author. I think when I asked what alternatives have you considered to set the overall prior weights, actually I think what the author meant was, and what I misunderstood was, how do you weigh the prior versus the data, or is that inbuilt in the system, or how did you do that?
That's a very good question, and I'm always trying to avoid weighting different losses. So the very convenient thing about the second work on the 3D reconstruction is that we found basically a way for every one of these priors that we could build in without adding another lambda term that needs tuning, and then you have 7 different lambdas, and you really have a hard time to decide, is it 0.2, is it 0.4? So the flipping is basically just randomly applying the flipping to the internal albedo and depth map, which does not need any weighting factor at all. And as I said before, this confidence on the reconstruction is self-balancing. So you don't need any weight at all, because you're just minimizing this kind of Gaussian loss, and then having the sigma in the normalizing term of the Gaussian and also in the exponent means that it's finding the optimal weight itself. So I think that's a very interesting way to dealing with these kind of things, to find a way to introduce your priors such that you don't need to add another regularizer on top, because often also these regularizers are fighting against each other, but of course it's not always possible. Sometimes we also have to introduce a lambda and then just find out what the best way is to deal with it.
Fantastic. I'll take this next question to be the last one. So there's clearly a lot of interest. Can you provide some more details which exact outputs of the CNN are used for clustering the labels? Most occurrences of features, kernels, or more?
Yes, I can quickly jump to that part of the presentation. This is probably the best slide for it. So the only thing that we're using for the clustering is the probability distribution that the network already outputs. So this P of Y given X. And then the idea is basically that you want to assign your labels such that they align as much to what the network already predicted as possible. So if the network really thinks this image is in cluster 1972, then you also want to give this image to this cluster. However, you have the second constraint that all the images in this case need to be equidistributed, or if you have a different distribution, follow the distribution of cluster sizes. And what the optimal transport solver does is basically gives you this assignment that is as close as possible to the network output, but still follows your prior of the distribution.
Brilliant. Very good answer. Well, Christian, thank you very much indeed. That was an amazing talk.
Thank you.
In our own administrative thing, there is a survey. If you participated in this seminar, and if you could give us feedback how we can make this better and improve, that would be highly appreciated. I think it will be attached to the email, and if you're on Zoom, it's also in that group chat. Anyhow, Christian, thank you very much again, and hope to see everyone very soon. Take care.
Thank you very much. Bye.